Great. Good afternoon, everyone. So you're joining the Lifecycle Energy and Related Impacts of Buildings webinar series. Today, you're joining the Building Technologies Office's webinar on innovative building materials. I'm Sven Mumme, and I'm a technology manager for the Building Envelope R&D subprogram. And I look forward to this webinar on a new topic for BTO. And we're really excited to see so many people joining us. Before we jump into things, I wanted to let you know that this webinar is being recorded. So you're all muted now, and you're welcome to stay muted. But if you turn your webcam on or speak, that is your consent to being included in the webinar recording that will be posted after the webinar is complete on the BTO website. Next slide, please. So here's the agenda for today. As I said, I'm Sven Mumme, and I will give some opening remarks, and then I will hand it over to my colleague, Leila Fadali, who will be giving an introduction to lifecycle carbon in buildings. And then we have an exciting panel of experts we have invited to join the discussion today. So let me quickly introduce them. Will Shribar is an associate professor at the University of Colorado at Boulder, whose experimental and computational material science research integrates biology and polymer and cement chemistry to create responsive biomimetic and or living materials for the built environment. He's the author of numerous technical journal papers, book chapters, and conference proceedings, and is a founding co-chair of the Embodied Carbon Network. Christy Gamble is Director of Sustainability at CarbonCure Technologies. CarbonCure is a leading movement to reduce the carbon footprint of the concrete industry and thereby help reduce embodied carbon in the built environment. Christy acts as a liaison between the sustainable design community and the concrete industry in order to promote the manufacturing and subsequent usage of lower carbon concrete. Next, we have Bing Hu. He's a professor at the University of Maryland and co-founder of InventWood. He has published over 300 research papers, including recent developments on wood-based nanotechnologies to create replacements for plastic, steels, and other materials. We have Junho Wang, is a professor at the University of Maryland and co-director of the Center for Environmental Energy and Engineering. He's a world-renowned expert on energy efficiency and innovative energy systems research in the field of refrigeration and air conditioning, developing energy-efficient heat pump systems and alternative refrigerants for air conditioning systems, as well as researching enhanced CO2 systems. And finally, we have Will Shribar, Associate Professor at CU Boulder, who will be, I already introduced Will. So you got the topics here that they'll be presenting. And then finally, we have a Q&A session that Carl Shapiro, one of my colleagues at BTO, will be leading at the end of the webinar. So please stick around for the whole discussion because after these great presentations, I'm pretty sure we'll have some good, Q&A at the end. Next slide, please. So as I said, this is a webinar in a series. We are in webinar number 3 of a 5 webinar series on the topic of building lifecycle impacts. Today, we'll be discussing innovative building materials. We started the series with an overview webinar about a month ago, and 2 weeks ago, discussed challenges of assessing lifecycle impacts of buildings, which I encourage you to check out. They've been on the BTO website. And we have 2 more exciting webinars coming down the pike. So so we're hoping that you'll be able to join us for those as well. If you're unable to attend, those will be posted on our BTO website. Next slide, please. Okay, so we have a poll question to get us started. So what industry are you from? So take a minute, select one of the bullets here to see who's joining us here today. Okay, so it looks like we have a good mix of people here from from federal, state, and local governments, as well as a good representation on consulting and corporate. Okay, great. So I wanted to give you a brief introduction to the Buildings Technology Office. So at BTO, at the Department of Energy, is focused on energy efficiency in buildings. Buildings consume more energy than any other sector. Close to 40% of all energy usage, primary energy usage. And also approximately 75% of all electricity used is in buildings. It's a big deal, and that's what we're tackling on. Next slide, please. So at the Buildings Technology Office, we work on a broad spectrum of activities to advance energy efficiency. So that includes R&D to advance energy efficiency and demand flexibility, validation, testing, and market integration activities in both residential and commercial buildings, as well as codes and standards work. So some of that is, our regulatory authority to come up with binding minimum efficiency standards and work on those, as well as technical assistance on the code side. Next. So here is an example of some of the work we've been working on. Here is a refrigerator of about 40 years ago. Back then, many of you will be familiar. This will be a familiar site. They're small, expensive to purchase, expensive to operate. But today, you have refrigerators that have more features, are less expensive to buy, less expensive to operate, and bigger. Next slide, please. So in this, go back, please. So this is exactly what we want to see in the world of energy efficiency: to save money in energy, give you more services. And there are quite a few additional examples, such as in LED lighting and low-E windows, and we're working on market transformation activities to bring more such innovation to light. Next slide, please. So I want to talk about our impacts on a national scale. So this is just looking at energy efficiency standards that have been completed through 2016. These are expected to save 142 quadrillion BTUs through 2030. So that's more energy than the entire nation consumes in 1 year. So energy efficiency matters a whole lot. It is saving energy and money and has a large impact on climate change. And we're proud of our work at BTO. Next slide, please. So we're a missing part of this picture. I mean, a lot of our work is focused on operational energy efficiency, and that's we haven't focused as much on embodied energy and life cycle carbon, and that's exactly what we're here to talk about today. BTO does not, we haven't been looking at this. So we've done some research, and so we've been thinking a lot that what we can do to have a more comprehensive picture of the impacts we can have in buildings. So today's discussion is going to be about innovations in building materials, from basic research to startups. We want to examine innovative building materials, both structural and non-structural, from a variety of perspectives. BTO has mostly looked at materials from an operational energy savings perspective and demand flexibility, as I mentioned. So I'm really looking forward to exploring materials more holistically, see where the focus has been and where it may move to the future. So with this, I'll pass it on to Leila.
Thank you, Sven. So before I continue, I have a piece of business, which is that I'm a AAAS Policy Fellow in the Building Technologies Office at the Department of Energy, but I'm acting in my personal capacity today, and everything that I say represents my own view and does not represent the views of the Department of Energy, the U.S. government, or the organizations associated with my fellowship, AAAS and ORISE. With that out of the way, as Sven was saying, the work that we've been doing in BTO has been having an impact, but there's part of the picture that we've been missing. But in particular, our office has been focusing on the emissions that are associated with operating buildings. But you can see there's a significant slice of the emissions pie that comes from building construction. Next slide. It's really important that we address this because global building stock is expected to more than double by 2060, and if we want to be able to address the emissions that come from constructing those new buildings, then we need to act now. Next slide. Okay, so we want to look at the whole picture, which is life cycle carbon. Life cycle carbon refers to the carbon emissions associated with all stages of building life. It includes both operational carbon, which has been our office's historical focus, and embodied carbon, which is the carbon emissions associated with all these other stages of a building's life, from resource extraction, extracting raw materials through to end of life. Next slide. So this webinar series is about exploring questions like where are the biggest opportunities, where can our office have the biggest impact, what types of buildings should we think about, what types of materials, what parts of the life cycle. Next slide. In our preliminary investigations into the life cycle carbon of buildings, we found that envelope and appliances were the majority of life cycle energy. So you can see in this data, appliances account for about 20% of life cycle energy. And that actually is a place where our office has done work in the past with appliances and refrigerants. So we're going to hear about that today. And you can also see that envelope accounts for about half of life cycle energy. So that was a place where we thought we could really get involved and maybe have a difference, make a difference. So that's why we're having this webinar on innovative building materials today. With that, I will hand it over to our first panelist. So Will, take it away.
Great, thanks so much, Leila. Let's see if I can. I think you'll be able to see this. All right, yeah, good morning, everybody. First, thank you to BTO for inviting me to be part of this panel. I'm Dr. Will Schrubar. I'm an associate professor at the University of Colorado Boulder. I'm also founder and managing director of Minus Materials and Aureus Earth. We're of course here today because construction has a carbon problem. Steel and concrete production alone contributes more than 11% of global greenhouse gas emissions. So we're of course talking about, my main concern really for the industry is this upfront carbon emissions, this pulse of emissions associated with the manufacture, transport, and installation of construction materials that happens even before we flip on the lights or the HVAC. So this is an excellent graphic that shows traditional carbon emitting building material manufacture like steel or concrete. The process starts with mining and manufacturing and construction, really what we call life cycle stages A1 through A5, this like pulse of emissions. These materials are stored in the building for a given period of time, but by then the damage is done. So harmful emissions remain in the atmosphere beyond 2050. Many companies are trying to reduce these upfront emissions. CarbonCure, for example, you'll hear from Christy, can reduce the emissions associated with concrete by 5 to 8%. There are other strategies too that can reduce concrete emissions by 40 to 50%. But really the main point here is that there is benefit to these reductions, but emissions are still emissions. And so reductions are really just avoiding additional emissions of CO2 into the atmosphere, which doesn't really help us remove carbon from the atmosphere and reverse climate change. So how do we get to carbon neutrality or carbon negativity? We really have to look to balance carbon emitting materials with carbon storing materials. So nature has already evolved really the most effective carbon removal mechanism on the planet. Of course, I'm talking about photosynthesis. And so for these materials, there's an initial photosynthetic drawdown that occurs, drawing down carbon before harvest and manufacturing and construction. And if we lock these materials up, if we lock that carbon up in a building, there is meaningful carbon storage for decades. So other companies are making mineralized products too, like aggregates, precast concrete, and fillers using atmospheric CO2. It's a very similar concept, but I'm going to be focusing on biomaterials for the remainder of the presentation. So why is this a good strategy? It's because all photosynthetic biomass, every tree, plant, seed, and algae cell sequesters and stores carbon. In fact, 1 kilogram of grown biomass draws down about 1.8 kilograms of CO2. So the tremendous opportunity at hand for the building industry is for us to really incentivize the use of building materials that rapidly sequester and store carbon. In terms of opportunities that I want to describe for you, it really is to paint a picture of the current landscape of next generation biomaterials. My lab is working on a variety of what I would consider bleeding edge biomaterial technologies. We engineer materials from plants and wood and algae, even lichen, and even proteins. But I would classify these as lab scale innovations, and I want to instead highlight today some cutting edge biomaterial innovations available to the industry today. Number one is, of course, sustainably harvested wood. Sustainably harvested is the key phrase here, since the goal is to keep the carbon balance in the forest. No product really represents the biomaterials revolution in construction better than mass timber. So mass timber or cross-laminated timber are massive structural panels made from dimensional lumber. And yes, there is substantial carbon storage in these materials, but there is also substantial carbon avoidance in these buildings when we replace concrete frame and steel frame structures in mid-rise construction, which is now enabled by the building codes. Wood is great, but I think that we can go beyond wood and think about other biological materials that demonstrate promise for carbon storage. There are significant opportunities for rapidly grown materials from straw and other agricultural residues. So we should invest in companies making high performance building materials out of these materials. So there's a statistic that the carbon drawn down and stored in straw every single year equates to the emissions from transportation in the United States. We of course feed the straw to cows, which convert it to methane, which makes it actually worse. But the goal would be to make materials and lock that carbon up for decades. Similarly, there's a host of agricultural residues Sunflower stalks are a good example that are left to decompose after harvest. And some of that carbon can be tilled and stored in the soil for sure, but not much is, we're not able to do that with all of the carbon. The rest is emitted back into the atmosphere. So locking that up into high performance building materials is a grand opportunity. There are other examples with bamboo, which is a strong, tough, fast growing grass, and even industrial hemp. Hemp is one of the fastest growing plants on earth, and we're now able to cultivate it in the US thanks to the 2014 Farm Bill. It had been illegal to do so since the 1920s and 30s. And hemp lime insulation, or hempcrete, is both fireproof and it's lightweight. It's already a common building material in Europe and parts of Canada. My lab just published a study that proved some formulations of hempcrete insulation are actually carbon storing. So again, another grand opportunity for these types of materials. And then there's algae, no stranger, I'm sure, many of you are no stranger to algae, which is already cultivated for food, fuels, and pharmaceuticals. My lab at the University of Colorado sees a tremendous opportunity to grow carbon storing building materials using algae technology. So for example, we are already growing carbon storing fillers and aggregates for concrete. So one of my PhD students and I recently founded Minus Materials, a startup focused on scaling this technology in partnership with mid and large scale algae cultivators. What we're trying to do is, if you use, trying to get the industry to use these rapidly grown mineral fillers and aggregates to really transform concrete into a carbon sink. My lab has gotten quite a bit of press lately. We're really indebted to the New York Times and Science Friday, and so continue to keep a pulse on what we're doing in the lab, because we're trying to convert some of these into commercialized technologies that we ultimately spin out. And we're not the only ones thinking about algae. Algae is great. You'll find some great examples of integrating algae with building systems to have on-site energy and fuel production or contribute to diffuse daylighting. You can have on-site food production and, of course, carbon storage. This is a great opportunity for BTO and others in the industry to look into further. I'd like to end with 3 primary challenges facing the construction industry as it relates to low carbon and carbon storing materials market. The first is risk of using these new materials and achieving cost parity. So the challenge is, how do we incentivize the use of carbon storing building materials? And while we can wait for policy, I'm proud to be a co-founder of Aureus Earth, another startup company that is really trying to tackle this problem using economics. So AE is creating the world's first carbon marketplace for building and infrastructure projects. We're contracting with emitters that are looking to spend their carbon dollar on decarbonization, and we see an opportunity to use that dollar to incentivize the use of low carbon and carbon storing building materials. The second challenge, which I think we can talk about, this is a great transition to the Q&A and discussion. Second challenge relates to data, the limited availability of EPDs, or environmental product declarations, and the differences in LCA tools to quantify embodied carbon, as well as the disparities in the underlying data of these tools. Relatedly, understanding industry averages and benchmarking is a persistent challenge. And finally, maybe because I'm an educator, there's a challenge related to education, availability of resources, and training the next generation of architects, engineers, and manufacturers. Decarbonization will be one of construction's greatest challenges it has ever faced, and we just need to prepare the next generation for the long road ahead. So I hope you walk away thinking that, although it might not be easy, we can transform the built environment from a carbon emitter into a carbon sink. I, for one, am confident that we can do so. So with that, thanks again to BTO for having me here today. I'll look forward to the Q&A after the remainder of the presentations. I think I'll transition now to Christy.
Thanks, Will. My screen should be sharing right now, reducing the carbon footprint of concrete. So my name is Christy Gamble. I'm the Senior Director of Sustainability with CarbonCure Technologies, and that was such a good segue into this presentation. So CarbonCure is on a mission to reduce the carbon footprint of the concrete industry by turning concrete into a carbon sink. So we are currently working with concrete producers all across the US and across the globe to utilize carbon dioxide as a beneficial material in concrete production in order to reduce its carbon footprint. So with that, first of all, as we've learned, embodied carbon is expected to account for nearly 50% of the total carbon emissions from new construction between now and the year 2060. And now concrete happens to be one of the largest contributors to embodied carbon, if not the largest. This has to do with the fact that concrete is the most abundant man-made material in the world. It's actually the second most abundant material, period, after water. So because of its abundance, cement, the ingredient that is used to make concrete, happens to contribute to about 7% of the world's CO2 emissions. So it does mean that concrete being one of the largest contributors to embodied carbon, if you want to reduce embodied carbon and you want to look at a place to start, you could start with concrete. Because of the large emissions associated with concrete, there's also a lot of opportunity to improve those emissions and to reduce embodied carbon overall. So CarbonCure is a technology innovator. We have developed a technology that utilizes carbon dioxide in concrete. So our technology beneficially repurposes carbon dioxide to reduce the carbon footprint of concrete without compromising the concrete's performance. And I'll explain a little bit about how that technology works in the next couple of minutes. First of all, we have nearly 300 concrete plants worldwide using the technology. So a couple of international locations, including Singapore and Japan. Across the US, we've partnered with a number of the state's leading concrete producers who have installed our technology at their concrete plants to then reduce the carbon footprint of the concretes that they are providing to construction projects. The graph that you see here, this map of dots, is expanding rapidly as our technology has been validated by these leaders in the industry and is accelerating throughout the industry as we speak. So how it works is the CO2 is captured and distributed to concrete plants by industrial gas suppliers. So CarbonCure does not capture CO2. It's sourced by industrial gas suppliers who capture CO2 from typically fertilizer and ethanol plants, and then purify and supply that CO2 to the carbonated beverage industry. So that's right, if you're drinking a Coca-Cola right now, that's CO2 that probably came from fertilizer, which is delicious, I know. But how that industry works right now is that this capture is happening already. It's just that the CO2 remains a gas and eventually makes its way to the atmosphere. So there's no environmental benefit to it. We tap into that existing reliable CO2 supply source, and when we introduce it into concrete, it chemically converts into a mineral and we get rid of it. So I'll explain that in a minute. Going back to the process, the CO2 supplier installs a tank, which you can see here, at every concrete plant where our technology is installed. In this tank, the CO2 exists as a liquid because it's under pressure. So the CO2 supplier will come by on a regular basis and refill that tank with CO2. Our technology is a precise metering and injection system. We're delivering a precise dosage of this CO2 into the concrete. This integrates with existing equipment that exists at every concrete plant. It's integrated with the batching software, so it's all automated and intelligent. We're taking the CO2 from the tank and introducing a precise amount into the concrete as it's being mixed. When that happens, when CO2 goes into a concrete mix, a chemical reaction begins to occur immediately, where CO2 and calcium ions that come from cement attract each other. It's like a magnetic attraction that occurs in the presence of water. And these two materials attract and bind into calcium carbonate, which is essentially limestone. So we've turned that CO2 into a limestone mineral. Where the value of this comes in is that because this is happening at a chemistry level, the minerals that are resulting are these tiny nano-sized particles. So these tiny nano minerals bind to cement grains inside of concrete mixes and increase the surface area of cement, This gives more surface area for the bond that occurs between cement and the materials around it to bind to. So it ultimately makes this cement more efficient. More efficient cement means higher strength. So if you do nothing else but just add a precise dose of CO2, we get about a 10% improvement to strength at 28 days. And this allows our concrete partners to adjust their concrete mixes. Cement is the material that gives concrete its strength. Cement is also the most carbon-intensive material in concrete and the most expensive. What we're looking at here is the bread and butter of our technology and our solution. In the light, so looking at the right side of the graph, the light gray bar shows the strength of a concrete mix in a control mix. The dark gray bar shows that same mix with a reduction in cement. As you'd expect, if you take cement out of the mix, you see a drop in strength. The orange bar shows the same mix with a reduction in cement and CO2 added. CO2 has brought the strength back up to where it was before. This is an example of an optimized mix, where the concrete QC team has said, how much cement can I take out of this mix while maintaining the same compressive strength as I had before? Typically, it's about a 5% reduction to cement content that's enabled while maintaining compressive strength. And all other properties are maintained. So the concrete that's delivered to the site is the exact same concrete that you would otherwise expect. If you didn't know CarbonCure was in there, you wouldn't be able to tell. It's the same workability, the same hardened properties, so durability and density it's all the same. And I can go into that into a lot of detail, but for the sake of time, I'll just say take a look on our website for further information, or I'm happy to field questions later. So in terms of how much CO2 can be saved, it's about 25 pounds of CO2 per cubic yard of concrete that's either mineralized or avoided by reducing the cement content. And on a case-by-case basis, this really adds up. So to date, over 7.5 million cubic yards of concrete have been delivered to construction projects. Here's an example of one project, a mid-rise building in Atlanta, Georgia, where 1.5 million pounds of CO2 were saved on this development. That's equivalent to over 800 acres of forest land absorbing CO2 for a year. And we've demonstrated and replicated this on many other types of projects. So ranging from LinkedIn campus in San Francisco, universities in Indianapolis, in Atlanta, the Georgia Aquarium, an airport paving in Calgary. So as you can see, a large range of projects across a large range of climates and conditions and locations. One project you don't see on here, construction just started, but it has been announced publicly, is Amazon's HQ2 headquarters is being constructed with CarbonCure concrete. And we're seeing a lot of uptake from departments of transportation and municipalities. So departments of transportation, federal, municipal, statewide procurements is a long road and a long process that requires a lot of testing and validation. So we've gone through that process with a handful of DOTs, and more of that is underway. We're seeing some early acceptance and strong indications for further procurement opportunities. So how can you reduce concrete's carbon impact? Well, I cannot stress enough that communication is the biggest key. The amount of times that I've seen a communication gap being the reason why concrete is delivered to site that has not been optimized for lower carbon it's a common problem, unfortunately. So communicate that this is important to you, design for the strengths you need. Use supplementary cementitious materials or low carbon cement. These are complementary strategies to CarbonCure, so you can stack the carbon benefits. Remove unnecessary prescriptive concrete specs and consider performance-based concrete specs instead. So this encourages sustainable innovation. Finally, specify and or approve CO2 mineralized concrete. So to wrap things up, a building or infrastructure project may save as much CO2 as hundreds, if not thousands of acres of trees absorb over a year. So who knew that building with concrete could be like planting trees? Thank you very much. I'm happy to hand it off now.
Hello. Okay, thanks for the invitation. It's my great pleasure to introduce our work on wood-based structural material for building applications. So I think, as pointed out, we're facing great ground sustainability challenges. There are billions of tons of CO2 emitted to the environment, and the millions of tons of plastic produced, and many of the products end up in the landfill or ocean. And as pointed out by this Millennium Project, sustainability is actually #1 challenge we're facing in the future. So now maybe trees can be actually part of the solution. Through the photosynthesis, the trees can take the CO2 and release oxygen. So the trees are actually a living CO2 sequestration system. And after its growth, it can continue to serve as carbon storage material, right? So for the use, so it's found the longer the carbon is stored in wood, the better for this purpose. So that's I think a building play a very important role if we try to take advantage to address this carbon cycle, carbon emission issues. So so there are a lot of trees. They are like on average we have about 400 trees per person. Even though we have so many trees, but the usage of this material has been increased dramatically. That's why we see a lot of trees, and we hear a lot of news about forest fires every year. So I think the idea is that even though this material is sustainable, sustainability alone itself cannot drive tremendous increase of this the use of this material. So so the idea is that can we dramatically improve the performance of the wood, maybe 10x 20x improvement, so that we can actually create a paradigm shift in using this forest materials, and can promote better forest use and better forest management. So for example, can we make a wood as strong as steel, or like maybe best concrete, for example, and so that will promote the forest use. It's not about cutting the trees. As we're cutting the trees, we're going to plant more. Yeah. So as long as the industry is motivated, I think we kind of have a very healthy cycle. So now the challenge is, how can we make a wood significantly better in terms of performance? So I think nanoscience and nanoengineering can really help in this regard. We just need to look at the wood in a very different length scale, in a much smaller scale, that actually give us better properties. So if you look at a tree, it has a well-defined growth direction. Along this direction, you have these hollow fibers, and they are the fibers of your paper material, and the diameter is about 50 to 100 micron, and so that dimension has been explored by material scientists over the past centuries and so on. So now in the past 20 years, I think people now start to look into the nano feature of the cell. Actually this material is made of not nanofibers with a diameter of about 5 nanometer instead of 50 microns, right? And no matter how complex the wood structure is, depends on the wood species, actually the building block is very similar. It's actually very similar for bamboo, for some other grass and so on. Yeah. So it's actually very commonly found in almost any kind of biomaterials. So if we can focus on using the nanofiber as the building block, I think we can actually engineer a lot of new properties. And I'm going to give you 2 quick examples. It shows basically the smaller the better, right? And we're not the first one to use these nanofibers. In Europe, in Asia countries, in Canada as well, there are a lot of opportunities. Many scientists are working on this nanofibers. And most people are basically taking the fiber apart and put them back into microscopic structures, but there are a lot of water and energy used there. So eventually we have to make this material manufacturable at no cost. So my group has been working on this material in the past 10 years. We're looking actually from a very different angle. We want to use this nanofiber, but we don't want to break it this part using a lot of water and energy and put it back and have to remove all the water. So using the wood as a scaffold, engineer inside the wood, open up the nano channels, and hopefully we can benefit from these nanofibers without using too much water and energy. So related to building, my group has been invented quite a few technologies, such as transparent wood. This is actually much better than glass in terms of thermal insulation properties, and nano wood for thermal insulation materials is actually funded by SWAN for the phase 2 SPR project. And super wood, this is actually about how can we make wood as strong as steel, and we reported this paper about 2 years ago. At that time we can achieve 600 megapart. Now actually we can achieve 1000 megapart, and I think it's actually better than many steels used in buildings. And also radiative cooling wood that you can cool the house without using any electricity. So I think these are all possible because now we're looking at this material in a very different than the nano scale, in a very small nanoscale. So actually they will give you much more flexibility. For example, for super wood, you have more bonding sites, and I'm going to give you a quick example. So this is about a super wood, as strong as steel, but 6 times lighter. And actually, the innovation is very straightforward. Once we understand, we have to get down to this nanofiber size. So we invent this process. We have to get rid of some of the lignin, so they get the fibers exposed, and then at the same time the material becomes very soft, so you can densify it. So it's very different with the previous densification techniques. People usually can get up to 200 megapart at most, or 300, but now we can actually get to 600 and 1 gigapart. So process is highly scalable and involving the chemical and the mechanical process. This is the typical curve, and this is the regular wood. This is what the super wood is about. And when we normalized by the by the mass, it's also lightweight material. It's very important for buildings as well. And this is how the material looks like. It's much more densified, and you really can take advantage of the nanofibers alignment in an original wood. So this is something actually, if you take the bottom-up approach, the approach taking a lot of water and energy, even that you cannot get this kind of alignment. So I think working on wood, taking the wood as an entire structure, I think we have a lot of advantage, in that regard. So we can bend them, it's much higher bending strengths, compression strengths, and this process is actually universal. Yeah. So as I said, no matter how different the trees are, the building blocks are the same. Yeah, they are different because of the microstructure. If we densify them, it actually almost become the same material. The strength is even better than the strongest wood you can find in nature, because now we have a further densification. So of course, we want to focus on cheap, straight trees, like give an easy process. And we have been actually improving this process, and also many other tricks as well to scale up the manufacturing. The other point is more related to what I said. The super wood, I think, it can be a very important component for buildings to replace steel, to enable a lot of even building designs if we want to make different kind of shapes. And we are actually able to engineer wood further to get us different shapes and so on. Another one is this cooling wood. I know my time is up. Let me try to be quick. In this case, is really to take the advantage of the cold universe, so that we can cool the house by the thermal emission in the infrared. This is your house, and you have a problem, and you have this window that is transparent, so the thermal energy can emit out through this window. Okay, so ideally you shouldn't have a heating problem, but you have this because of the sun is so hot. It's really a lot of solar energy. So the trick is really to reflect the solar energy back, still maintain the infrared emission. So that means you have to have a very white material to reflect the solar energy, and have a very black material to emit the energy. So you have to have a emissivity very different in the solar spectrum and in the infrared. So in the solar spectrum, you want to make it white, so you can really bounce back the energy. There's not much energy absorbed to your house. You basically make wood very white. At the same time, this material has a lot of hydroxide groups, a lot of functional groups. They can vibrate and they can emit the energy. And they absorb the energy, they also emit the energy. So in that case, this material is actually very black, even though we cannot see it. So in the end of the day, if you integrate everything, this material actually can emit the energy out in the first certain regions, especially in the summer. While the radiation cooling can be applied. Yeah. Now, in general, cooling is much more difficult than heating thermodynamically. So this material is also a structural material, so it's very strong, and the strength is up to 400 megapascal, right? So we through collaboration with Yanina here, and we've done modeling to see what kind of energy impact you have. Of course, this material shouldn't be used for the regions with cold water, but there are a lot of places, they have long period of hot summer, and the performance is much, and cooling effect is much less in the cold temperature. So it works in right away. So the last thing I want to point out is that we are trying to advance wood technology by dramatically improve the performance, but at the same time, there are existing infrastructure from the wood industry, from the paper industry, that we can hopefully integrate or can apply, even benefit from the manufacturing infrastructure to take our innovation, and to manufacture for building applications as well as other, like such as transportation and so on. Okay, I think with that I would like to conclude. Want to have to ask a question during the Q&A section. So next, I think John Hong with Marina.
We can't hear you. I think you might be muted. Can you try unmuting?
Okay,
Oh, we can hear you now.
okay, sorry, sorry about that. Again, yeah, this is Huang. I'm a research professor at University of Maryland. Can you see my screen too?
Yes.
Okay, good. And then I'm serving as an associate director of the Center for Environmental Energy Engineering. I'll be continuing what Bing Hu mentioned about the thermal performance of the material itself, but I can extend it to the system level life cycle CO2 emissions. So I worked with the IIR for 4 years to develop a harmonized life cycle climate performance potential evaluation tool, considering direct emission part as well as the indirect emission part. For the direct emission part, we consider refrigerant leakages during the normal operations time and during the irregular emissions and during the services at the end of the life and while the product is transported. And also we consider atmospheric degradation of the refrigerant and their byproduct also contribute to the global warming. So we need to consider that. The second part is the indirect emission part, which consists of energy consumption by the system throughout the lifetime, and also energy to make the material and the system and component, and also to make the refrigerant itself, and also transport of the system component as well, and also the energy consumed during the end of the life recycling process, the recovery of the system processes. So we consider all the aspects of the emission from direct to indirect, from the beginning of the product to the end of the life product, how much will be the total life cycle carbon emission is. Then tool we develop is the Excel basis for residential heat pump. Here's the example showing the input the need to be provided by the user. As an example, you need to choose a different refrigerant, charging amount, unit weight, annual leakage rate. For example, is a 4%, end of the life leakages, lifetime of the system, we consider 15 years. and then material itself. I'm going to talk about it later. And then when heating system will be turned up and so on. And then you need to provide cooling and heating performances based upon the test data or based upon the modern result according to the HERI standard 210 and 240. So once you provide this information, then this tool will calculate total emission from the system in absolute values and as well as the relative values as shown in this slide as an example. So as you can see from the left-hand side, this tool provides carbon emission from 5 different locations in the US by considering different climate zones. And it also gives you breakdown of individual contribution, including total, the direct emission through annual emission, end of the life emission, and indirect emission by energy consumption, equipment manufacturing, end of the life, and refrigerant emission. So cooling and heating system also utilize the materials, for example, steel, aluminum, copper, plastics, and so on. The material can be virgin material or recycled material or a mix. So we can consider any combination of those to consider actual the case. But this contribution is end up to equipment manufacturing here, which is end up to be about 0.4% of the total carbon emissions. So therefore, instead of considering embodied carbon of the material itself, energy consumption is a major contribution that we need to consider, since they are responsible for 90 to, let's say, 85% of the total emissions. So therefore, energy consumption is very important. Energy efficiency is very important. So therefore, we did a sensitivity study. What if we are reducing global warming potential of the refrigerant? How much CO2 can be reduced? Right now, R410A is used, that is HFC, as a refrigerant of the cooling system. Then global warming potential is about 2,200. And now we are developing much lower global warming potential fluid as shown in this table as example. Then, for example, when you are using R32 as example, then the global warming potential can be substantially reduced. And when you're using propane, of course, it's much more. However, it's more flammable. So when you're reducing global warming potential from 2,200 to like a 500 ranges, then total carbon emission can be reduced by around 8%. However, when you're improving energy efficiency by 10% or 20%, then we can almost reduce carbon emission by 20%. So therefore, reducing energy consumption is very important, which means thermal performance of the building material is essential to minimizing carbon emission from the cooling and heating systems. So in addition to this, the system, the carbon emission evaluations, then Dr. Anderson and expert members suggested to consider enhanced and localized circumstances, especially reflecting the different situation in developing countries. So as example shown in this picture bottom left, you see all the outlet units are installed at once. Then there's a cascade effect of the thermal stratification so that top floor unit will see much higher ambient temperature than the lower floor, so that they are consuming more energies. Then architecture design, people don't like this kind of appearance, so that they want to hide the cooling and heating system inside the nice looking balconies. Then air is trapped so that system will consume much more energies. So LOP estimated CO2 emission, additional CO2 emission can be increased almost 48%. So therefore, installation and architecture design is also very, very important, in addition to improving energy efficiency of the system and also improving thermal performance of the building materials. So with that, I can quickly summarize it. Through the IIR, which is the International Institute of Refrigeration, we developed the harmonized LCCP guidelines in year 2016 that recommends how to perform the LCCP calculations for heat pump system, and it also provides data sources for individual components. So lessons are energy consumption is a main contributor of the carbon emission from the system, followed by the annual refrigerant leakages. And enhanced and localized LCCP is also very, very important for the practical purposes. And our thermal engineers will develop low global warming potential refrigerant to be applied so that that portion will be contributing about 8% of the carbon emission minimization. Also will be improving energy efficiencies to minimize the energy consumption from the system. That can be reducing carbon emission by about 20%. But building material scientists, as you are, if you can improve the building thermal performance by 70%, actually you can save much more than what you can do. So that I'm expecting more euro of the lower in the future. Okay, that's what I have here. Okay, I'll turn on the microphone to the organizer.
Great, thanks so much to all of our wonderful speakers. We have a few minutes here remaining to answer the questions before we wrap up. And I'll invite all of you to turn back on your videos for the Q&A session. And as a reminder to the audience, please use the Q&A feature to ask a question. So my name is Carl Shapiro, and I'll be the moderator for the Q&A session. And again, just a little bit of business. I'm a AAAS Policy Fellow in the Building Technologies Office at the Department of Energy. But today I'm acting in a personal capacity, and everything I say represents my view and does not represent the Department of Energy, the US government, or the organizations associated with my fellowship, AAAS and ORISE. All right, with that done, we want to kick off the Q&A session. And I want to pose this question first to all of our panelists, and whoever wants to jump in first can jump in. So the first question is, we have seen a chicken and egg issue with many innovative building materials. And so a single project may be interested, but can't afford to bring it to the area because of costs. So how can we overcome this challenge in the future?
This is Christy Gamble here from CarbonCure. I'll jump in on my perspective of that, which is that I would start with education is so key to creating a movement to make sure that a request or an interest in reduced carbon is not just one project only. The more demand that's out there, the more likely it is for a product to come to a market. That being said, it's certainly a challenge, and it's important for solutions to find ways to be cost efficient so that it's feasible for more options. And I realize that doesn't really answer your question because it is a very tough question to answer overall.
Yeah, I'll add, so this is Will, great question. I'll add that, I think in the future, we're gonna be looking more toward regional manufacturing of some of these innovative building materials to really lower transportation emissions and also lower cost. And second is that it is important to take into account that transportation in terms of quantifying the upfront embodied carbon, because there are cutoff distances for certain materials like CLT, like mass timber, where it doesn't make sense in some geographic locations. You're doing more harm than good than transporting. The third point I'll make is to reference Aureus Earth. This is exactly what we're trying to do with the carbon marketplace, to try to incentivize the use and specification of these materials where they would otherwise be cost prohibitive.
I think you're muted. Looks like we lost Ping. Yunho, do you want to jump in on this question?
Yeah, I think I was, delivering a little bit different aspects, which is the equipment side or system side. Again, the material is very important to minimize the cooling and heating load of the building itself. That can have a significant impact to the carbon emission minimizations. So, of course, we'll do our work to improve the energy efficiency of the system to reduce the carbon emission by 30%. but again, you can do double emission reduction than what it can do.
Great, and Bing, we might be able to hear you now if you want to jump back in. Still can't hear you. I guess we'll just move on to the next question, but thanks for your insights for the rest of the panelists. So there were also a few questions about scalability of innovative materials. The first question was directed at Will, but it's basically, they're interested in thinking about how to scale some of these materials, especially for agricultural residues, when thinking about the trade-offs between land use, agricultural crops, or feed for biofuels. And if you could comment a little bit on that. And then there was another question, which I think feeds into this a little bit for Bing, which was, would innovative wood production processes would that allow for increased recycling of used wood, and would that allow for conservation of existing trees? So we'll jump to Will and then try to head to Bing and see if this audio works.
Yeah, of course. I'll try to make this relatively quick. So I'll go back to my regional focus, where there should be for these types of material technologies to be very hyper regional, with understanding what biomass is generated specifically as an agricultural residue. So not purposefully growing materials just for construction. I give the example of the sunflower stalks that are largely left to degrade out in the fields. That's really good quality biomass that could be used. Certainly some of that is already used for biofuels. So then it just becomes, whether or not there's an economic incentive to make materials out of it. And then Carl, the second part of your question was.
Yeah, sorry, the second part was, I guess mostly for Bing, about whether innovative wood production processes would allow for recycling of existing wood.
Okay, so I sorry, I muted myself. I couldn't find. Now I hope you can hear me okay.
Yeah.
I was trying to add to where I think the distributed manufacturing, the use will be very important. Yeah, and many of this biomaterial can be produced locally, and if we can manufacture them locally, and then you can avoid and use locally, you can really avoid a lot of transportation going back and forth, right? I mean, the second part is really, cost always associated with manufacturing. I mean, all these technologies, especially invented in the university labs, yeah. If we need to have an impact, we have to manufacture, and then we have to, maybe find different ways to, instead of manufacture everything by yourself, maybe be integrated with the existing manufacturing infrastructure, and that's how I view it. And the question about whether we can use recycled wood, or people even ask me, can we use the half-burned wood in California, for example, right? So I mean, if it's if it's not fully carbonized, yeah, and I think the process we're doing here should be applicable. So if it's dead wood, or the wood that is sinking underwater for a long time, I think it's still doable, yeah. But if it's fully carbonized, I think that we cannot do much about that.
All right, great. So I think we're about out of time at this point, but thank you all for submitting your questions. Sorry we weren't able to get to all of your questions. There are a lot of technical, really insightful things that showed up on the question box, so I'm looking forward to hearing more about that in the future. But I'd like to thank all of our speakers for this wonderful conversation. And to wrap up, I'll remind you that we have 2 remaining webinars in the Building Lifecycle Impacts DOA webinar series. So we're looking forward to seeing you in the weeks to come at these 2 additional events. Thanks so much, everyone, and goodbye.
Okay, thank you.
Thank you. Bye-bye.
Bye.